Hello, CS325 525 simulation and modeling students. Um, it's customary in online classes for the professor to make a little introductory video. I am Professor Glass. Um, my office is in Gellerson at 122, and there's two offices there. I'm the one on the left. And I'm generally available, and unless I'm really busy on something, um, I will be happy to talk if you just come by or you email to me, etc. Um, and I'm hoping that even though this is an online class, we can turn this into a kind of cooperative enterprise where we're all working towards, exploring and having fun with these and learning about these notions of simulation and how to do it. Um, there is a book, which you will have seen in the bookstore, agent-based and um, individual-based modeling, okay, by Fishback and Grimm. Um, and it uses a programming language called NetLogo, which we'll be getting into very quickly, but not right now. Um, right now, what you should be doing is reading chapter 1. And what I'm going to do for the next couple of minutes is give you a little bit of context. Chapter 1 talks about agent-based simulation, and it describes the um, cycle of producing and refining a model. And the main idea being that you need to know what it is you're trying to measure, what you're trying to optimize, what characteristic of the system that you are simulating are the ones that are of interest to you and possibly affect your outcomes, and those are the ones that you put into your model. Um, what the book does not do is give you a little bit of context. So I will do that, referring to historical examples that get you from the idea of modeling to a what I hope is a good intuitive feeling for why this agent-based computer modeling might actually be a useful tool, why we want to go there. Um, the first thing I'll start with is really classic differential equation models of predators and prey. Traditionally that might be foxes and rabbits, or it might be, mongoose and snake, depending upon your cultural organization or orientation. Um, and let me quick show you the classic equations for this are these ones here. Um, and the main idea is if X is going to be the density of rabbits, the number of rabbits per square mile in the territory, and Y will be the number of foxes per square mile. And to make ask ourselves, what's the time behavior? What affects the density of rabbits? Well, one of them is that rabbits will breed like rabbits. Um, and the more rabbits per square mile you have, actually, the faster the population will probably grow. So the time derivative, d rabbits dt, or d rabbit density dt, will be positively associated with the rabbit density. And how often rabbits encounter foxes. So that's the rabbit density times the fox density, gives us a density of rabbit-fox interactions, and that's negative. That decreases the number of rabbits per, with time. All right. So that's the simple differential equation for the number of rabbits. Number of foxes is similar. We imagine the foxes just naturally just die off in the absence of any rabbits. They have nothing to eat. So the the foxes dt is going to be a negative number in the absence of rabbits, just letting them go. They'll they'll get old and die, or they'll starve and they'll die. And fox rabbit interactions again will increase the number of foxes. Okay, so that's y prime. So this gives you two differential equations. Okay, that tell you the behavior of foxes and rabbits over time. And then famously, you can get oscillatory behavior where the foxes sort of overgraze, the number of rabbits go down, there's not enough to eat, the number of foxes go down, rabbits then increase like that. Okay, that's classic differential equation modeling. All right. I'm now going to go back to computer work from about 50 years ago. And this was a famous set of computer modeling that experiments that were done to talk about fire stations in New York City. Specifically, it was in the Bronx. Um, and there were about 2,000 fire boxes where people could walk up and pull the alarm um, scattered around the, street corners of the Bronx. Um, there were some number of fire stations, and they wanted to answer questions. As they emphasize in the book, the question you're trying to answer is going to define how you build the simulation. Um, Questions like how much material do we have? How many um, two different types of fire trucks are called engines and ladders. How many of them do we have in the fire station? Um, and then given the statistical variety of fire calls that happen, how often does a call come in and there's nothing there? The equipment we need is out on another fire. Or what's how long does it take? How can we optimize the response time given where the fire stations are, given where the fire calls are coming from? Okay, how can we do that? Those are the kinds of questions they were trying to answer. Um, and that kind I'll go to that paper right now, one page of that paper. This is showing you some of the properties they measured. They have historical data about calls from, okay, for fires. Okay, and for some number of them are false alarms. All right. Um, and to a false alarm, one engine and one ladder truck both go, and it's usually over in about 5 minutes for each. Okay, they point out here you don't need both, but you didn't know it was a false alarm. Okay, and then what they call EG emergencies, non-structural fires, transportation fires. Okay, those are usually take about 18 minutes. There's so many percent of the calls that come in like that. So you have this statistical data, and there's time data in here too. These calls are happening this frequently, okay, at these times of days. And you could build a statistical model of these fire calls arriving. And then what you could do is you could, if you wanted, you could just say, well, if I have one fire station and it's got this many engines and this many ladder trucks, um, you can compute from the statistical properties of the distribution of the calls. You could compute what's the spread of, how many times does this call come in, 1 minute or 5 minutes or 10 minutes after the previous call, what types of calls come in. And you could actually compute using statistical computations how often a call is going to come in and you don't have the equipment. It's out at another fire. Okay. That's, you can do that. Um, but you didn't really need something like agent-based modeling to do that. But suppose you've got the whole Bronx, 2,500 fireboxes, you've got some number of fire stations, okay? You've got the map of, where's the nearest fire station, where's the next nearest fire station in case the first one didn't have, okay? And now doing all that statistical computation breaks down, okay? Basically, we got to do is build a game, like a computer game. So you're going to build a computer game. Here's my fire stations. Here's what they have inside of them. You throw the dice. You run the random number generator. You generate the first fire, and then you generate the next fire according to your randomly, inter-arrival times. And you move you say these engines ladders from this guy are busy. They're busy for this minute. The next call comes in. Okay. Oh, this one's out. Like that, right? When you get a complicated enough scenario, you can no longer just do the statistical computations. What you do is you play the game. You build a game and you play it for a long time, simulated time. And from that, you can measure how often call comes in, something's not available, how often, how much, your delays are. Okay. If I redistribute the trucks and ladders, how how often, whatever metric we're using, quality metrics we're using for fire response, for equipment utilization, okay, whatever your metrics are, okay, you can then run the simulation for long enough and then get the answers. All right. And that was not done by solving these things analytically or numerically. That was done by playing the game. Okay. Happens to be called discrete event simulation. It's very similar to the agent-based simulation, which you're going to be doing. All right. It's kind of the precursor that both types of simulation are in pretty heavy use right now. The agent-based simulation tends to be easy enough to do that you can just do that instead of the discrete event simulation to get the same thing. They really are pretty close. But that is, I hope, gives you an intuitive feel for how we got to agent-based simulation and why you might want to do it. It's a system which is complicated enough that you can't just convolve a couple of statistical distributions or solve a differential equation. Um, you've got stuff going on, the game that needs to be played, and then you run that enough times or for long enough, and you can measure the behavior. So that's where chapter one, in a certain sense, begins. Chapter one talks about the agent-based simulation, but it never really describes why you need to do it. But that's why you need to do it. So you go off and read chapter one, and I will stop this recording.